I can see we are now 17. We will start. And I want to believe others will join us as we move on. So we are still looking at antihistamine blockers. I want to believe you'll be able to, I hope you'll be able to finish all the classes today. I mean, all the classes of the H1 blockers today, and then, H1 blockers, H1 blockers today. That means generation 1, generation 2, and generation 3. So that now, the next perhaps 1-2 classes, we look at the H2 and the PPIs. So if I'm not wrong, last time you were able to go up to the propylamines, or the archelamines. I hope that's where we went up to, and we did mention that the archelamines can be further divided into 2 subclasses, whereby we have the one which is saturated, like the chlorpheniramine, pheniramine, and so on, brompheniramine, and then we have the unsaturated, where we have a double bond between the X carbon or the central carbon and the next carbon. And because of that double bond, whenever you introduce double bond into drug molecules or into any other organic molecules, you expect to have geometric isomerism. Geometric isomerism is whereby different groups are distributed differently. In other words, remember, geometric isomerism is also a type of stereoisomerism, and it is a type of stereoisomerism by the arrangement of the bulky groups. And of course, we do have the Z and the E, the Z representing the Cs, and we call it the Z because in these particular drugs, if you look at them, the different groups are not the same. The different groups, there are none of those groups which are the same. We call it cis when you have some of those groups attached to the adjacent carbons are usually repeated, and that therefore cis. But if you look at drug molecules, none of those groups, you can say the groups that are attached to the 2 adjacent carbon atoms can be WXYZ. They are not similar. And therefore, we give it a specific name Z or Z, the Z isomers. So the Z is the same as the cis, yes. The Z is the same as the cis, and the E is the same as the trans. When you talk about the trans, this is where the bulky groups are on opposite sides. And more often than not, when you have bulky groups on opposite sides, you do have the advantage of lower steric hydrons or lower repulsions. Because when you have 2 bulky groups on the same side, they'll be trying to repel each other. And for them to repel each other, you must put energy in that molecule, so the molecule be unstable because it will be at a high energy level. So we did mention for both the 2 compounds that we have, which are unsaturated, trifluridine and pyrobutamine, we did mention that the E isomer, which is a trans isomer, has also more, it better fits the receptor. Do remember, we are saying it better fits the receptor because it will have that lesser repulsions. It will give us the correct size, which we said is between 5 and 6 angstrom, for it to optimally interact with the receptor. And I think that is how the farthest we went. And we did look at trifluridine and pyrobutamine. They have unsaturation in the propylamine side chain and therefore exist as geometric isomers, that group there. And we did mention, if you look at this isomer, remember here there is a hydrogen. That one has a hydrogen. And because of this nitrogen here, nitrogen has much higher atomic number, has a higher atomic number, I believe. And therefore, you find that that atom is much bigger than, this group is much bigger than that group. So in this group is big. So this big group and the hydrogen are on the same side. And then on this other side, this group here, in this other side, if you look at this carbon is attached to this. And whenever you have attachment to somewhere where you have a double bond, then it is like that carbon is attached to carbon. So this also is a big group. So this is a big group, and compared, so this is also a big group. But when you compare with this one, so you have that big group and that big group being, because the E, we have said the E is a trans isomer, so we expect this group and this group to be on opposite sides. So that group and this huge group are on opposite side, and that's why we are saying that is triploridine. When you look at this one, that is a big group, and that is also the big group, and both of them are on the same side, and that is the Z or the Z, all the cis isomer. If you look at this group here, this carbon, it is joined the same way. So we will look at the next atom, and I believe what's the atomic mass of what's the atomic number of nitrogen? What's the atomic number of nitrogen? 7, isn't it? I believe. So I believe the atomic number of nitrogen is bigger than that of carbon, and that is what makes this ring bigger or much bulkier than that ring. So when this ring and this group, when this ring here and this group here are on opposite sides, then that is the on opposite side, that will be the trans isomer. When this group and this group are on the same side, that is what we are calling. When we look at this, let us look at it again, because we are saying that group. So which group are we saying is the big one? You have that group and this group. You can see are on the same side, and this is the E isomer. Remember, the E isomer is the same as the E isomer actually represents the trans. The E is the same as the trans. So if these two rings are on the same side and it's the trans, that means this group, as I have said, is much, much bigger than this. So in bigger ring and that bigger ring are on opposite side, and that is a trans isomer. Now, when we come again to the other one is the triploridine, we are saying that in both cases the E isomer is more potent. So even when we look at triploridine, we still expect that the E isomer will be the more potent. Again, remember the E isomer is where the two big groups are on opposite sides. So if you look at these two groups here now, please appreciate the presence of that carbon there. This carbon here are different, because this carbon is attached to two hydrogens. And because if you look at this, we are looking at this carbon here, and we must look at the first carbon, the double bonded carbon is attached to. So if you look at this double bonded carbon, it's attached to this CH2 group here. On this other side, it is attached to a carbon which is double bonded. And I have said, whenever you have a carbon which is double bonded, that atom that is bonded to it, it's like it's bonded atoms, because when you talk about a double bond, it means carbon double bonded to a carbon. It's like two bonds. So therefore, whenever you find a double bond, that compound that has a double bond is considered to be attached to a bigger group than the one like this one here, which is attached to a hydrogen. So we can consider, remember I said I would confirm the structure of pyroridine, and indeed pyroridine goes to the compounds, the ethanolamines, whereby we bring back the benzyl group, and pyroridine does not have, unlike the other alkyl derivatives, does not have a pyridine ring. So we are therefore saying this group is the bigger group. This group is a bigger group. So if you look at that big group here is a hydrogen are on the same side with that hydrogen, and then this smaller group are on the same side with this other group. So we are saying this is a bigger group when we compare these two. Group is on the same side with hydrogen, so definitely therefore that's why we are saying that is the E isomer, where the big groups are on opposite side. This is the big group there, and this is the big group, and you can see they're on opposite side because here we have an hydrogen. And I have explained the reason why this difference is occurring is that we are considering this CH2, this CH2 here. If you look at triploridine is the two rings are directly attached to this carbon, but in pyroridine it's a benzyl ring, so this carbon must be considered, and the the weight of this carbon and the weight of this carbon will be different. This will be much bulkier than that one because of the double bond, as I've explained, and therefore this is the E triploridine, and that is the Z pyrobutamine, and that is the Z pyrobutamine. I have explained why. And we are saying, therefore, the E pyrobutamine will also be more potent than the Z pyrobutamine. And as we have explained, this is because of the distance. This is because when you have the E-pyrobutamine, it gives you the necessary distance between the groups, or the necessary distance for the final molecule which is needed for attachment to the receptor, because we require 5 to 6 angstroms for that molecule to be able to bind the receptor. The alkylamines have significant less CNS depressant effects, and the benzhydryl ethers of ethanolamines, so less SH1 blockers. These compounds, they are SH1 and antihistamines. These compounds have long half-lives and extended duration of actions. We expect the long half-lives because of the bulkiness of these drugs. And because they are bulky, they have a large hydrocarbon portion. That hydrocarbon portion must be metabolized to give them some water polarity or water solubility for them to be removed from the body. They have decreased antiemetic effects and decreased anticholinergic properties compared to the ethanolamines. Say the ethanolamines, because of that oxygen, they have more structural similarity with acetylcholine, and therefore once they cross the BBB, they will go for the acetylcholine receptor more than these other drugs. And therefore once they go for the acetylcholine receptor, remember they are antagonists because of their big size. Although they have structural resemblance with the cholinergics, when they go for the acetylcholine, not trigger that receptor, they will block that receptor, and therefore the anticholinergic effect. So we are saying, again, because of the structure of these groups drugs, they will have lower anticholinergic effects as compared to the ethanolamines. And dealkylation is a major pathway with the corresponding secondary and primary amines, as well as the parent drug being found in the plasma. Of course, when you look at all these drugs, they do have alkyl amino groups, and therefore they can undergo oxidative end dealkylation. Let us look at the propylamine. We are still looking at the propylamines or the alkylamines, and if you look at both of this, the unsaturated, we're looking at the unsaturated alkylamines. You can see the introduction of the pyroridine group. That is a pyroridine group, and even when you look at the pyrobutamine and with the unsaturation, you still have the pyroridine group. And of interest is that, of course, our 1, 2, 3, our 3 carbon atoms are actually aliphatic. They are not part of the cyclic ring. It is only the nitrogen which is part of the pyroridine ring, and we had said with retention of activity. And of course, when we look at that nitrogen, we see it is attached to slightly bulkier groups, because this, if you look at that nitrogen, that's a CH2. If you look at this nitrogen, CH2. But we didn't mention whenever the substituent is part of a ring, there is constraint, and we still do have good activity. So of importance to note is that both the unsaturated alkylamines do have the pyroridino group. So the N substituted, they do have the N substitute. The N substitute is a pyroridino group, or the pyroridine ring. It fits the structural requirements of 5 to 6 angstroms between the tertiary amine and the aromatic ring. And of course, that's what we have said, because of the constraint. Whenever part of a cyclic ring, there's a little bit of constraint, and therefore the compound is still able to meet the requirement for the structural requirement or the requirement for size. Plus, it contributes to the lipid water partition coefficient. You can see it has just a nitrogen. The nitrogen contributes to water solubility, and the other bulkier, the other 4 carbon atoms will contribute to lipid solubility. So that pyroridine ring is good enough. It contributes a lipid water partition coefficient, and therefore drug still gives this drug good lipid solubility for it to penetrate the relevant lipid membranes. Parasubstitution of the phenyl ring cis to the nitrogen increases potency, but decreases potency if on the phenyl which is trans to the nitrogen. Let us see whether that is obeyed. So again, we are saying, if you look at, let's start with the triploridine, you will see this substitution para. See, this is para, and it is which is on the cis to the pyroridine nitrogen. So this ring and that ring are on the same side. So we are saying para substitution on the phenyl ring, which is cis to the pyridino nitrogen. That increases activity. If the substitution was on the other ring for tripyridine, you'll be substituting on the pyridine ring. There will be a so let us also look at the other one. We are saying again, if you look at this is our E. You can see this is a pyridino group. It is also on the same cis side. So again, para substitution on this phenyl ring, not that phenyl ring, again increases activity. Substitution of the para phenyl ring decreases activity. So you can see it also agrees for both compounds. So that's what that statement is saying. Para substituents on the phenyl cis to the, this is of course the pyridino nitrogen, increase potency, but decrease potency even the phenyl trans to the nitrogen. I hope it's clear. It was therefore concluded that the two aromatic groups have a different function in the interaction of the receptor. So these two groups, they require specific substitution, and therefore they must be interacting with the receptor slightly different. Again, remember I did mention these bulky groups might not bind the specific area where histamine binds, but they will bind the surrounding area, the surrounding environment of where the histamine binds, to give us a better binding, a better bond, and therefore resulting in antagonistic activity. So again, we had looked at this, and I've now looked at it properly, and it's now easy to understand. This drug, this ring is showing us actually pyrobutamine. You can see that is the chloro group para. This is the CH. So this is the pyrobutamine. And we have said if we were to look at the E, we are saying E is the trans. And E being the trans, this ring and this ring are on the same side, because we have said this is the smaller group. This is a smaller ring. So that smaller ring and this one are on the same side for our E isomer. For our Z isomer, then you have, if you are to look at the distance between the Z isomers, would be when this ring and that ring are on the same side. If you have this ring and that ring, remember this is a big ring and that is big ring. If they are on the same side, that will be isomer, or the cis isomer when the two big rings are on the same side. And if these two big rings are on the same side for pyrobutamine, you can see we are therefore saying there must, this when you have the Z isomer, the Z isomer is when they are these are on the same side, and it will require, because of the repulsion forces, it will require these rings to be very far from each other. For the cis isomer, when this and this are on the same side, the distance is smaller. So all we are saying is that the distance must be maintained. That distance must be maintained, because if that distance is not maintained, then you find that the drug will not bind the receptor. And that's why we are saying we do require the E isomer. You require the E isomer, where this being, these are bulky group. This is a lesser bulky group, where this lesser bulky group and that one are on the same side. And because, as we are saying, they are the lesser bulkier one, then they will not have a very big distance as compared if this and this are on the same side, then the distance must be very long, and that will give us problems. So again, we are saying the cis isomer, even when we look at the diagram, the cis isomer gives us the correct, not the Z isomer, sorry. So the trans isomer, which is the E isomer, gives us the correct distance whereby the optimally bind the receptor. So that is those were the alkylamine derivatives, and we move on. And please note where we have looked at the ethylene diamines. We've looked at ethanolamines. We stressed about the ethanolamines. We have two categories. We have the propanoamines and we have the ethanolamines, whereby, of course, one, there is a slight, there's introduction in the propanoamines, like masking, there is introduction of, again, of optical isomerism, and we did mention which isomer has better activity. Then we have gone to alkylamines, and we are stressing again that where you have unsaturation, again, stereochemistry is very important. When you answer your questions, please note, Stereochemistry and structure-activity relationships are two different things. Like now I'm looking at your answers, and some of you, when you ask for this effect of stereochemistry, you talk about relationship. Structure-activity relationship is different. Stereochemistry is just the arrangement, the spatial arrangement of the specific groups. Spatial arrangement of those specific groups in space. That is a stereochemistry. It can either be optical isomerism or it can be geometric isomerism. Don't waste your time talking about SAR because you will just get a 0. And then along the way, you expect that you will also mention stereochemistry. That is not the way to answer the question. If you answer of stereochemistry, remember stereochemistry is the spatial arrangement of that molecule in space. So what affects the spatial arrangement? It is spatial arrangement. It is either there is geometric isomerism or there is optical isomerism. Those two are the ones that will affect how those molecules are arranged. Or you have one group carrying the alpha orientation and another group carrying the beta orientation. Those are the ones that will affect the arrangement of that molecule in space. So that is quite important. Don't mix structure-activity relationship. Structure-activity relationship is now where you keep saying, if I change this molecule, if I change this group attached to this position, it can lead to better activity. Like what we have said, a para-substitution. Para-substitution will improve activity. That is SAR. So please don't confuse the two. So we have now looked at those three groups here on the first category, and the fourth category is the piperazine, structure related to the ethylene diamines, and I believe that is, and of course, and the ethanolamines, they are all structurally related. They have significant and cholinergic effects used mainly to treat vertigo, nausea, and vomiting, especially for those people who have a lot of problems when they are traveling. We do have people when they are traveling, they vomit a lot. These are some of the drugs that are used for such problems. I think I had enlarged too much. So piperazine, cyclizine, both nitrogens are basic, and you can see why. Look at this, these are piperazine derivatives, and none of those nitrogens is attached to a phenyl ring. And therefore, the nitrogens have retained their lone pair of electrons, and therefore they can, of course, be used for bonding. But I believe, of course, the one which is at the end, the one which has lesser steric hydrons, will be the one which will be more basic, because it will allow for the ready access of the proton. The terminal nitrogen is more basic due to less steric hydrons and no electron withdrawing groups in the vicinity. About the vicinity, not directly attached. The other one is just vicinity, but the none of those groups directly attached. They have moderate potency, the slow onset, and prolonged duration of action, moderate sedation, and low anticholinergic effects. They also possess peripheral and central anti-nausea activity, thus they are used as antiemetic, antivertigo, and anti-nausea products. So this is an important one. They have central anti-nausea, and that's why I have said for people who travel and vomit a lot, these drugs, and those drugs can help them to prevent them from travel sickness. So when we look at these drugs again, remember this is their general structure. So remember we are saying they are piperazine. This is the piperazine ring. That's the piperazine ring. You can see this nitrogen. It is not directly attached. That's what we are saying. Not directly attached to any of the phenyl rings. It's attached to a carbon ring, and that's why we have said this nitrogen might be lesser, might be slightly lesser in its basicity because of the vicinity of the phenyl rings within the vicinity, and of course the steric hydrons, which is on this side. So this nitrogen here, you will have much higher. You have much higher basicity because the nitrogen, the lone pair of electrons are much easier to access. So when we look at these drugs, we have like cyclizine, and all we are saying R2. So you can see that they can differ with either R1 or R2. R1 here or R2 there. Those which will be substituted there. Again, para, you can note in all of them, the rings are the same, so it doesn't matter which. So para substitution, or also on the piperazine ring, you can also get para substitution on N substitution. So when you talk about cyclizine, is when this is a methyl group, and that is not substituted. Chlorcyclazine, again, is just a chloro group, and that is a methyl group. So then we can see again the names can give you an idea of the compound you expect. The meclizine is that, again, it is a substitution of chlorcyclazine. You maintain your chloro group there. Then at this position, you put a slightly bulkier group. So at that position, you put a benzyl. So you join it with the CH2 and a methyl substituted go a toluene. That's a toluene group. So that is a slightly bulkier group. So I would expect that the basicity of that drug also to be a little bit lower. Of course, you can see the first substitution is a CH2, so that at least gives a bit of there is a little bit, there is decrease. Instead of this being directly attached to that nitrogen, there is still a CH2, which therefore that nitrogen still retains its basicity. Then you have, again, you can see buclizine. From, again, the name, you can see you have a butyl group there. Again, you have a CH2. And then you have the phenyl ring, and you can see the butyl, the tert butyl group there. Tert butyl group there, again increasing, helping to increase the lipid solubility. And that is why these drugs, they still have high lipid solubility, will cross the BBB and give us activity. That one. And then the other one is hydroxyzine. I'm mentioning the ones which are quite important. When you look at hydroxyzine, again, it still retains the chloro group. So the chloro group seems to have an influence on activity. And then you can see here, at that position is a little different. Group at that position is a little different. And the group we get at that position, when we look at hydroxyzine, hydroxyzine is also the precursor for cetirizine. So you can see they have also drawn cetirizine. And the only difference is that for cetirizine, the alcohol of hydroxyzine has been oxidized to the carboxylic group. And because of that, then cetirizine moves to the second generation, whereas hydroxyzine is in the first generation. Because once you convert this to a carboxylic group, you reduce the lipid solubility, you increase the water solubility, the drug does not penetrate the BBB readily, and therefore it's mainly retained in the periphery and reducing the central activity. So that it is important that this is put here just for purposes of us to compare that the group that is found in hydroxyzine, very, very similar to the group that is found in cetirizine. Of course, because that one is an alcohol and the other is a carboxylic group. And the minute you see the carboxylic group, you should be able to know what the difference is in terms of polarity, in terms here of toxicity, that you expect cetirizine to have less central toxicity compared to hydroxyzine. So these are just the structures again. That is cyclazine, chlorcyclazine, meclizine, as we had done, hydroxyzine, buclazine. So that is just the structure drawn out. Piperazines, again, the same thing, meclizine, you can see that, hydroxyzine. So those are the same structures that we have drawn out again. So nothing different there. I think they have been drawn many times. Then we can note something about these drugs. As we have said, they are not majorly used as antihistamines, but as we have said, they're not majorly used for allergic reaction. Say they're used for vertigo or motion sickness. Cyclazine has only limited H1 blocking activity and used mainly in motion sickness. As we have said, chlorcyclazine has sufficient H1 antagonist activity due to the parachloro substitution. Again, parachloro substitution has the same effect as we have seen in the others. Meclizine and buclizine, again, meclizine and buclizine, remember it is their substituent on the N. It's actually N4 on the piperazine ring that is different, this being a methyl group, benzyl methyl group with a benzyl methyl substituted group, and this one being a benzyl butyl substituted group. Are also effective H1 antagonists used primarily as antinauseates in motion sickness and vertigo. They are highly lipophilic and have significant CNS properties. Highly lipophilic, and you can see why. Like the butyl has a butyl substituent, you have a butyl substituent plus a benzyl group. Meclizine has a methyl substituent plus again a benzyl group. much, much higher lipid solubility, but they are also effective H1 antagonists. Hydroxyzine, even though a classic H1 blocker, possessing anticholinergic and CNS present, its major use includes the management of anxiety and tension associated with psychoneurosis as well as allergic conditions. So hydroxyzine will also found some other activity, so it can be used as an antidepressant. It can be used as an antidepressant, but it can also, and once it has such activity, then more often than not, you will selectively use it for the antidepressant activity and not for the antihistamine activity. It also has a lot of sedation. It's a mild antidepressant, and it is also has a sedation, because we are saying it will cause a BBB, cause some sedation. Cetirizine is an acid analog of hydroxyzine. It has 6.5 times lower receptor affinity, and being a sweetion effect. We're going to look at it. It has lower CNS effects, and once it has a lower CNS effect, it is a sweet ion. It has a positive and a negative charge because of the carboxylic group. The carboxylic group can undergo ionization. It has a nitrogen, piperazine nitrogen. The piperazine nitrogen can be protonated. The carboxylic group can undergo ionization. It has sweet ion. It is sweet ionic. It has both the positive and the negative charge at the same time. And because of that sweet ionic presence, or because of the sweet property, then it will have lesser sedating effect. It will be less sedating than, it is less sedating than the first generation, and more often than not placed in the second generation. And we have said that less sedating effect is because it is a sweet ion, and being a sweet ion, it will have higher polarity, lesser ability to cross the BBI. And once it has lesser ability to cross the BBI, then it will give us better peripheral activity and better peripheral activity with lower toxic effects or CNS toxic effects. So that is what we have for the tricyclics. As I have said, they have other added advantage that they can be used for motion sickness, they can be used for vertigo, they can be anti-nauseating agents, and therefore they have that very important role. And mainly will be used for those purposes, those indications, rather than purely as antihistamines. From that, we move on to the tricyclics. I don't know whether you should move. I think it's better. Let me see that. I think I want to come to the prepare. Let us first of all look at, well, they are kind of the same because they are also cyclic. So let us just follow the order. It doesn't matter really. So we look at the tricyclics. Remember, when we talk about the tricyclics, it is where now the two phenyl rings, in all the drugs we have looked at, the phenyl rings were, and now we have the two phenyl rings being joined or being all fused together. The two rings being fused together, that is, there is a joining group. Then we have the three rings. So when we talk about the tricyclics, it is where the three rings are all joined together. And we can call this the dibenzocycloheptane. Dibenzocycloheptane is a dibenzocycloheptene because of the fact that it has a double bond. So these ones, you can have different rings depending on which drug you are talking about. This is where you have a thiophene. Again, we do have said the thiophene can be an isoster of the benzene ring, so that's just an SAR. The pyridine ring again can be an isoster of the phenyl ring. Again, that's just an SAR. So we can have, again, as we move on, these drugs, these ones, the kind of drugs, we will not study them there now. The dibenzodiazepines, these ones we will study them when we look at antidepressants. When now you introduce two, you have these two heteroatoms, these drugs are mainly as a typical antidepressant. So the ones we'll be looking at is like this one, and we also look at another class, the phenothiazines. We will also look at tricyclics, also the phenothiazines, where now this carbon is replaced with only one atom, which is a sulfur. So when this is replaced with a sulfur, and this is replaced, actually it's this one. When this is replaced with a sulfur and this is replaced a nitrogen, that will be the phenothiazine. So when we look at the tricyclics, mainly we look at the dibenzocycloheptanes, dibenzocycloheptenes, and even this, we also look at this one. When this one, we look at it whereby it is just there, that phenyl ring has been replaced. We'll also see an example of this in ketotifen, whereby that group has been changed to a thiophene. So we'll be able to get an example of that, the benzocycloheptapyridine. So the benzocycloheptapyridine, benzocycloheptathiophene. So we have an example of that. We'll have an example of that. We'll have an example of that, an example of that. And then, of course, we'll also look at the phenothiazines. In fact, it looks like we are starting with the phenothiazines. I have said the tricyclics will include that one, that one, that one, that one, and the phenothiazines. And as I've said, phenothiazines is where the CH2 group or ethylene moiety is replaced with a sulfur with retention of activity. So we start with the phenothiazines, and the first member of this class was the phenethazine, introduced in 1945. Phenethazine was our first group. And then, so let us look at that before we talk at the SAR. So when we look at this, as I have said, this Y becomes a sulfur. You see, when we look at the tricyclics, this Y, as we have seen in the previous groups, can be a CH2, and this be a carbon. Can be a CH2 to give us the dibenzocycloheptanes. Y can be a CH double bond CH, and this is a carbon to give us the dibenzocycloheptenes. So that's why we are saying those are the cyclics. Y can be a sulfur, and X can be a nitrogen to give us the phenothiazines. So I hope you understand. So that's why we are saying all of them are cyclic derivatives, because of the fact that you can't change the X and Y and get drugs. So I want to first of all look at the structures of the phenothiazines. So we are saying the first member was the phenethazine. So if you look at the phenethazine, as we have seen, you can see that. You can see it's a derivative. If you block this is a phenyl ring, that's a phenyl ring, that's a nitrogen. So you can see there's a structural derivative, or it has structural similarity with the ethylene diamines, whereby it has a structural similarity with the ethylene diamines, where that to a nitrogen and 1, 2. So it has a structural resemblance with the ethylene diamines. It is only that the two phenyl rings have been bridged with a sulfur to give us now the phenothiazines. The first one being phenethazine. So that with the two structure, the two carbon atoms there, and that structure. And you remember when we were looking at the general SARs, there is somewhere I said that it is only in the phenothiazines where branching increases antihistamine activity. And we did mention that if you do branching at the beta carbon, if you branch at the beta carbon, beta to the nitrogen, 1 alpha beta, then you increase activity. So phenethazine was the first, actually the prototype not to have adequate antihistamine activity. Structural modification was done to give us promethazine. So this is promethazine. And you can see the difference between promethazine. It retains, this structure retains the same structure requirements, general structure requirement, where the central atom is separated from the terminal nitrogen with 2 carbon atoms. That's what we had discussed. The terminal nitrogen is a tertiary amine. That is what we had discussed. We do groups there. That is what we have discussed. So this drug retains the general SARs. The only difference is that in the phenothiazine, branching at the beta carbon, as in promethazine, increases antihistamine activity. So branching at that position increased antihistamine activity, and that's when you go and why when you go out there, you find one of the drugs that can be used at 25 milligrams, because it also has serious sedation. It is also used the phenothiazine are used as major tranquilizers. They cause a lot of sedation, and therefore they are more often than not used in patients who have psychosis. You only need to do a bit of structural modification of the phenothiazine and you get the antipsychotic drugs. Again, we will do that later. So, but all we are saying, the phenothiazines with this kind of structural modification, whereby there is branching on the spacer position, they increase activity. Then you can also have trimeprazine. Remember, we did mention the two nitrogens can either be separated by 2 carbon atoms or 3 carbon atoms with retention of activity, as long as you maintain the branching at the beta carbon. So you can have trimeprazine, you can have promethazine, which are examples of the phenothiazines which have been found to have histamine activity. So that's why I wanted to mention, to show you those so that you can be able to appreciate when in case we mention any SAR, you appreciate increasing the side chain to 3 carbon decreases antihistamine potency, but increases dopamine antagonism. So again, although you can have the 3 carbons like in trimeprazine, that molecule will have much slightly lower antihistamine activity. Branching of the propyl side antihistamine potency, but decreases dopamine antagonism. And that is why trimeprazine, if you look at the structure we've seen of trimeprazine, yes, it's 3 carbon atoms, which decreases antihistamine activity. You branch, beta branching, decreasing dopamine activity and increasing the dopamine. The ones with dopamine activity are the ones which are used as antipsychotics. So trimeprazine has branching, has 3 carbon atoms, decreased activity, increased activity by branching, and therefore that drug can have antihistamine activity. They are used in allergic rhinitis, allergic conjunctivitis, dermatosis, and rheumatism. So again, they are used as anti-allergic drugs. So when now we look at this actually represents not just the phenothiazines, is representing the tricyclic antihistamines, where we can say X can be a carbon, it can be a CH. If X is a carbon, most probably there's a double bond outside here. Carbon, it can only be a C, we have a double bond here, or it can be a CH, or it can be a nitrogen. So X can be a carbon, a C, a CH, or a nitrogen. And we'll have enough examples of that. Y, which is this one, and we have already seen Y can be a CH2, it can be a sulfur. When it's a sulfur, then we have the phenothiazines, and X is a nitrogen. It can be an oxygen, it can be an NH, CH2O. It is most important for us when it's a CH2, because when X is a CH2, and this is a carbon, then we can have, when this is either a carbon or a CH, then we can have examples of drug like cycloheptadine, and these drugs are actually having antihistamine activity. So it can be a CH2 or CH double bond CH. That time, so Y can be a CH2, Y can be a CH double bond CH, and those drugs have been found to have antihistamine activity. The spacer we have already discussed. It can be 2 to 3 carbons. It can be 3, like in trimepramine. It can be 2, like in promethazine, with retention of activity. R1 and R2 can be methyl. So this one can be methyl, or they can be part of a heterocyclic ring, again with retention of activity. We've already mentioned that R1 and R2 can be part of a, even with the H1 and the other antihistamines with retention of activity, or but with maximum activity when we have them dimethyl amino group. So that is the general structure of the tricyclic antihistamines, and we have said of most important is when that can be a nitrogen, that can be a sulfur, giving us the phenothiazines. That can be a CH2 group, and that can be a carbon. It can be a CH, and we see those are the structures that we get when you have the piperidine derivatives. You have either CH2 or CH, and of course either a double bond or a single bond at that position. So the tricyclic antihistamines that we are going to look at will have those structures. Please note, these structures will be repeated again and again when we look at other drugs. As I have said, the phenothiazines are also antipsychotics. So even when you come and look at them as antipsychotics, sometimes also we get this structure changed slightly again to give us the tricyclic antidepressants. So please do remember the fact that the receptors that we are looking at are not highly selective. That's all we are saying. They are not highly selective. And as long as the molecule you are looking at, which resembles, which can bind the receptor, you find these drugs binding several receptors, and that is why also they have a lot of toxicity. Adrenergic effects, they will have sedation, they will have anticholinergic effects, because they are not selective for the histamine receptor, but have structural resemblance with other receptors, which they will bind but not trigger any activity, and therefore bring about antagonist activity. They differ from the antipsychotics. I've already mentioned antipsychotic phenothiazines. Antipsychotic phenothiazines are those that are used for psychosis, and mainly they differ because when you look at the antipsychotic phenothiazines, you will find that this position for the phenothiazines will have, but that is number one. Number two, there will be a chloro group, like chlorpromazine has a chloro group at that position, but you can see this one does not. So they will differ from the antipsychotic phenothiazine derivatives, in which the chain usually is 3. So for the antipsychotics, the spacer is usually 3 carbon atoms, and there is usually a substituent at position number 2. Is 3 carbon long, blanched, and usually without substituents in the aromatic ring. So that is they differ from the antipsychotic phenothiazine derivatives, in which the chain usually is 3 carbon long, they are unbranched, and usually they have, not without, they have a substituent in the phenyl ring. This without is wrong. So they differ from the antipsychotic phenothiazine, which the chain usually is 3 carbon atoms. They are usually unbranched and do have a substituent mainly at position number 2. And you see, when you look at the antipsychotics, almost all of them have a substituent at that position. So that is a major difference between the antipsychotic and the antihistamine. And therefore, because the difference is very minor, you can have a lot of toxicity, because when you give an antipsychotic, it can also bind another receptor which it was not supposed to bind. So that's the structural difference, the structural, general structure activity relationship of bicyclic antihistamines, even as we look